One of the tables I gave you in your binder, which is behind your periodic tables, is called the standard enthalpy of formation table. And if you look at it, it's got a bunch of values like this, where the symbol for standard enthalpy of formation is right there. Let's talk about what this means. First of all, the definition of standard enthalpy of formation is it's the energy absorbed or released when 1 mole of a compound forms from its pure elements. The symbol that is used has a couple different things in there that all mean standard enthalpy in formation. So first of all, the delta H is what means enthalpy, a change in heat. The fact that it's a formation reaction is noted with a little f there. And then the standard symbol you'll see written up above, and IB tends to use kind of a theta-like symbol, whereas if you look at it in other texts, you may see it as written like this, with a little degree symbol used instead. And that symbol is what means standard. The definition of standard is at 25 degrees Celsius, or 298 Kelvin, and 100 kPa, or 101 kPa, depending on the text that you're using or what version of the data booklet they use. So let's see how we apply this. I gave you, or I'm showing a part of the table here so that I can reference the values as I use it. So for example, if I was gonna write a formation reaction for HBr, I'm gonna show HBr on the right side of the arrow. If I'm being thorough, I'm gonna include the state symbol for HBr, which I can cheat my way to off of the chart here. And that will be a G for gas. It's forming from pure hydrogen and pure bromine. One of the things you need to ask yourself as you write this is it diatomic or is it not? So hydrogen, is it diatomic? It is, so I'm gonna use a 2. Bromine, is it diatomic? Also is, so I'm gonna use a 2. Putting the phases in there, H2 is a gas, Br2 is a liquid at room temperature. When I balance this reaction, because it is defined as 1 mole forming, I am not allowed to add anything here because that needs to be a 1. So I need to balance it some other way. I can do that with fractions. If I put a 1/2 in front of the H2, that's now just 1 hydrogen. And a 1/2 in front of the Br2, that's now 1 bromine. And now I have that reaction balanced. Suppose I ask you to write the formation reaction for aluminum chloride. Once again, we're gonna have AlCl3 as a product. AlCl3 doesn't happen to be an example that's on this chart, but most ionic compounds are solids under normal conditions. This is gonna form from aluminum and chlorine. Is aluminum diatomic? No. Is chlorine diatomic? Yes, so I'm gonna add a 2 there. Aluminum, I'm sure you're familiar with, at room temperature is a solid, and chlorine is a gas. To balance this reaction, I have 3 aluminums on the right and 2 aluminums on the left. So I'm gonna, since that's an odd number, I'm gonna multiply by 3 halves, and I have that reaction done. All right, one last example. We're gonna write the formation reaction, show the relevant delta H value for methanol, CH3OH. So we're gonna form CH3OH. Methanol at room temperature is a liquid. So I'm gonna indicate an L there. Now in this case, we have 3 elements we're making it from. It's got carbon, hydrogen, and oxygen. Carbon is not diatomic, hydrogen is, and oxygen is. Both hydrogen and oxygen are gas at room temperatures. Carbon is a solid at room temperature. Now, balancing this one, I'm sure you can see the carbons are already balanced. On the right, I have 4 hydrogens, so I'll use a 2 there, and 1 oxygen on the right, so I'll use a 1/2 there. It also said I'm supposed to show the relevant delta H value. So for this reaction, the relevant delta H value is the formation of CH3OH. That value is negative 238.6. And if you look at the units at the top of the table, you can see that it says kilojoules per mole. Actually, all of this is my answer. One thing you won't find on this table, notice that carbon isn't on here alone. Hydrogen isn't on here alone. Oxygen isn't on here alone. That's because the heat of formation for pure elements in their most common form is 0. So you won't find Al on the chart. You won't find Cl2 on the chart. You won't find O2 on the chart because they're all zeros. If I were to write a formation reaction for O2 forming from its pure elements, this would be my reaction. And it's logical that this reaction has no change in energy because nothing's actually changing. But this is something you want to remember whenever you come across, I can't find this on the chart, that's probably why, unless it's something you're being asked to solve for.